Okay, we've found that negative 2, 1 is an eigenvector with eigenvalue 1, and 1, 1 is an eigenvector with eigenvalue 4 for this matrix A equals 2, 2, 1, 3. This means if I go up to a x2 versus x1 coordinate space, that any vector, any multiple of the vector negative 2, 1, and this is intended to be the vector negative 2, 1, which means any vector that goes from the origin to any point on this line, when you do this transformation, will be mapped to itself. Okay? However, any vector that's along the line of the 1, 1 vector, where the eigenvalue is 4, now let me just put lambda equals 1 here, okay? Now any vector along the direction of this one, along the line through this one, any multiple of 1, 1, well, lambda equals 4, okay? So that if you have a vector from here to here, okay, it's going to go to a vector that's 4 times itself. So vector from here to here, and if you identify that with this point, will go to a vector that's here all the way down here. So in that sense, this point would map to this point. So I could kind of indicate that. I'm going to indicate it lightly. Okay, a vector from the origin to this point will map to a vector in the same direction, but 4 times as long, because the eigenvalue is 4. So that means it's going to map to a point. We can think of this point being mapped by the transformation to this point. Okay? On the other hand, any point on this line, same point right here, maps to itself. Okay? So along this line, space gets stretched by a factor of 4. Along this line, it stays where it is. Now, I want to find too much stuff laying around here. Okay, I'm going to draw a circle about the origin. Okay, I'm going to attempt to draw a circle. Let's just draw a circle, fairly small circle, because after all, I'm going to have to stretch this circle in one direction by a factor of 4. Okay, not a great circle, but it's not bad. Okay, now, points on this circle. The points on the lambda equals 1 line, the line along the eigenvector, negative 2, 1, whose eigenvalue is 1, will just stay where they are. So when I map those points, let's put the mapped points in, I guess this will contrast well here. We'll see how it contrasts with the purple. Okay. These 2 points under the transformation are going to stay where they are, because these 2 points are identified with a vector from the origin to here, okay, or from the origin to here, and those vectors are in the direction of negative 2, 1, and any multiple of negative 2, 1 maps to itself. Okay. Now, what about points on the circle that are in the direction, well, that are along the line defined by the eigenvector 1, 1 with eigenvalue 4? Well, that means a vector from here to here would map onto a vector in the same direction but 4 times as long, so this point would end up out here. Okay, so this point would map to here, and this point, well, this is kind of close to this point, but okay. This point's going to map to here. Okay, so how are we going to do that? What's going to happen to the space in between these lines, okay? Well, you know, you're going to get something that looks like this, sort of elliptical, okay? The mapping of any point, let's say this point here, okay? If I take this point, how do I get to this point? How do I define this point in terms of my eigenvectors? Well, I can move from here to here, and then move parallel to this, okay? So I could have a vector that goes from here to here, and a vector that goes from here to here, okay? This vector is parallel to my eigenvector, so it stays kind of where it is, but this vector is parallel to the eigenvector with eigenvalue 4. It's going to get 4 times as long, so it's going to come down here. So this point ends up mapping to here. Now, that's kind of a picture that we get with eigenvectors, and I'll elaborate on that a little bit more, but hopefully you get a general idea of, first of all, what an eigenvector is and how it stretches space along its own direction, how you solve for an eigenvector, and then how you could depict a transformation that has 2 eigenvectors in R2.